Every PC builder obsesses over their CPU and GPU, but the single most important layer in your entire system is something you literally never see, and if you cheaped out, it's quietly destroying your performance right now. Counterfeit thermal paste. A microscopic film of thermal paste sits between your processor and cooler, filling invisible gaps like grout between tiles so heat can actually escape. Seems simple, right? But here's the thing. $5 tube of fake paste can completely negate a $60 cooler upgrade. Counterfeit paste flooding online marketplaces measure as low as 1 to 2 WMK. For context, legitimate paste sit around 4 to 12 and liquid metals exceed 70. That counterfeit tube is basically silicone grease in a fancy outfit. The result? Your CPU runs 5 to 15 degrees hotter, triggering throttling that slashes your boost clocks by 2 to 400 mAh. A layer measured in fractions of a millimeter impacts your temps as much as swapping your entire cooler, and you literally cannot tell it's fake until your temps spike. But if you think fake paste is bad, wait until you see what happens when your storage cooks itself alive. NVMe drives are supposed to be the ultimate storage upgrade, but they have a dirty little secret. They literally slow themselves down on purpose. Thermal throttling. You copy a massive file, the transfer starts at a blazing 5,000 sounds BRS, and you feel like a genius. Then 20 seconds later, your speed absolutely tanks to 2,000 BS. You just got throttled. NVMe controllers hit around 70 degrees under sustained load, especially inside cramped cases, and the drive instantly cuts your speed by 30 to 60%, which, you know, is not ideal. Reviewers test these drives on open benches with perfect airflow. Your drive lives tucked under a roasting hot GPU or plastic motherboard shroud with zero breathing room. Under combined load, temperatures spike into the mid-80s. At that point, your fancy $3,500 MBS NVMe feels genuinely slower than a 550 MBAS SATA SSD. During long transfers, it started fast, then crawled, and you probably assumed the drive was defective. Turns out, no, it's just cooking alive, and the fix is embarrassingly simple. A $10 aluminum heatsink or pointing a fan anywhere near the drive prevents this entirely. But nobody talks about airflow for storage because storage isn't supposed to need it. At least your NVMe only throttles itself, unlike your motherboard, which can secretly throttle your entire CPU. Your motherboard's compatibility list is lying to you. It says your CPU is supported, and technically that's true, but it never promised your chip would actually run at full speed. The culprit is the VRM, and it's the invisible valve choking your processor right now. VRMs take the 12-volt power from your PSU and step it down to the tiny stable voltages your CPU actually needs to survive. Think of them like water pressure regulators in a building. Your high-end CPU can draw 200 to 250 watts sustained, spiking above 300 watts. Budget boards with 4 to 6 phases simply overheat, trying to push that much current, climbing above 100 degrees Celsius. So your motherboard quietly throttles your expensive CPU from 4.7 GHz down to 4.0 or 4.2 GHz under load, which is, you know, not ideal. Here's where it gets weird. Almost nobody monitors VRM temperatures by default. It is a total blind spot. So when two identical builds perform 15 to 20% differently, people blame the silicon lottery instead of the motherboard power delivery. Turns out, no, your chip isn't unlucky, it's just starving. But if you think invisible valves choking your CPU is bad, wait until you see what happens when you starve it of bandwidth. RAM channel population. Most people treat RAM slots like parking spaces. Drop your modules wherever they fit and call it a day. But those slots are highway lanes, and using one stick instead of two is the difference between a dual lane freeway and a single lane service road. Here's the thing. Dual channel DDR4 3200 delivers roughly 51.2 gigabytes of bandwidth. Single channel cuts that in half down to about 25.6 GB/s. With DDR5, dual channel can exceed 80-90 Gbps. Same capacity, same frequency, completely different throughput. You'll see 10-25% lower frame rates in memory-sensitive games, especially with integrated graphics. The invisible part is that many pre-built ship with a single stick to save cost. One 16G ADIAT module instead of two 8GB sticks. Looks identical on paper, runs at half bandwidth in reality. Users blame the CPU or GPU when benchmarks don't match published numbers, never suspecting the bottleneck is one memory lane instead of two. Even DIY builders install modules in adjacent slots because it looks symmetric, completely ignoring the motherboard manual that specifies alternating slots like A2 and B2 for dual channel operation. You can have a powerful CPU, a modern GPU, and plenty of RAM installed, yet still underperform online charts by double-digit percentages. The system feels less snappy, frame times fluctuate, and integrated GPU scenarios turn into slideshows. All because your data highway is running at half capacity. At least the RAM channel population is fixable with a screwdriver and 5 minutes, unlike the next invisible mistake, which involves how much power your system wastes as heat, even when it's barely doing anything. KESU efficiency curves. Here's the thing, nobody tells you about power supplies. Bigger is not always better. Most people shop for wattage alone, assuming a 1000W unit is automatically superior to a 650W unit, when in reality the sweet spot has almost nothing to do with the number on the box. Power supplies are most efficient at around 40 to 60% load, much like a car engine that gets optimal fuel economy at cruising speed rather than idling or redlining. Run your PSU too light or too hard and you're wasting electricity as heat, raising internal temperatures and quietly shortening component lifespan. An 80 plus gold PSU at 50% load hits around 90% efficiency. An 80 plus bronze unit at the same output drops to around 85% efficiency. That extra waste doesn't sound like much, but it's heat your case fans have to remove, and over hundreds of hours per year it adds up on your electricity bill and accelerates component aging. Here's where most people screw up. They build a system that pulls 350 watts under full gaming load, then buy a 1000W PSU because of future proofing. That 350W load represents only 35% of the PSU's capacity, dropping efficiency compared to a properly sized 550-650 W unit that would run the same system at 55-65% load, right in the efficiency sweet spot. At idle, that oversized PSU is running at 7 to 10% load, where efficiency can fall below 80%, meaning you're wasting power even browsing the web. More waste heat raises internal case temperatures, forcing CPU and GPU fans to spin faster and louder, and quietly aging capacitors and VRMs. Efficiency directly affects electricity bills, cooling demands, and long-term reliability, yet it's completely invisible on most spec sheets. But if you think invisible power losses are bad, wait until you see how invisible connector limitations can sabotage your brand new high refresh monitor. You spent thousands on a premium monitor, but a cheap cable is secretly making it worse. Legacy display ports. Every HDMI and DisplayPort version looks identical on the outside, but the rules governing them change drastically under the hood. Plug a 4K 120Hz display into an HDMI 1.4 port, and you get 4K at 30Hz or 1080p at 144Hz. That is it. HDMI 2.0 gets you 4K 60Hz, but ask it for 120Hz and it simply cannot comply. DisplayPort 1.2 handles 1440p 144Hz perfectly, while DisplayPort 1.4 pushes 4K 120Hz using display stream compression. But here is where it gets weird. Monitors auto-negotiate these connections, and they will silently compromise to make things work. If your GPU and monitor both claim 4K 120Hz over HDMI 2.0, the monitor might actually deliver it by dropping to 4.2 T-Neurochroma. Subsampling, that means it discards most of the color information for every other pixel. Text gets fuzzy, edges get fringed, everything looks slightly wrong, so you spend hours tweaking settings convinced your expensive new panel is defective. Turns out, no. Your identical looking ports just have completely different bandwidth ceilings, and the monitor chose blurry deception over a black screen, which which is, not ideal. And if you think identical ports with secret limits are frustrating, wait until you see what happens with the cables themselves. High-speed cable standards. Here's where things get weird. You have two USB-C cables that look absolutely identical, same connector, same thickness, same length, and one moves data at 40 gigabits per second, while the other caps out at 480 megabits per second. That's roughly 83 times faster, and the only way to tell them apart is microscopic text nobody reads. USB-C shape doesn't guarantee speed. The connector is just a physical plug. What matters is which standard the cable was built to, ranging from USB 2.0 at 480 megabits per second all the way to USB 4 at 40 gigabits per second. Thunderbolt cables need active electronics inside to maintain full speed, and passive cables beyond certain lengths fall back to 20 gigabits without telling you. Power delivery ranges from 60 to 100 plus watts, and if you grab a low-rated cable to charge your gaming laptop, it'll throttle or just can't sustain full load. The most painful example is external SSDs. You spend $150 on a drive capable of 1,000 plus megabytes per second, plug it in with a free cable from an old phone, and watch it crawl at 40 megabytes per second because that cable is USB 2.0. The system doesn't warn you, it just works badly and you blame the SSD. Here's the kicker. Partial failures are harder to diagnose than total failures. If a cable doesn't work at all, you swap it immediately. But when things work just not optimally, people blame the drive, the dock, the OS, anything except the $6 cable sabotaging $300 of hardware. At least you can see cables and replace them. Your SSD's internal write endurance is invisible until the day it isn't. SSD endurance ratings. Here's the thing about SSD endurance. It's the ticking time bomb that never actually explodes. Every consumer SSD comes with a TBW rating, terabytes written, and it sounds terrifying on paper. A typical 1 TB drive might be rated for 300 to 600 TBW before the warranty expires. That sounds finite, like a countdown timer to disaster, and it's led to years of paranoid advice about preserving your SSD by disabling features and treating the drive like a fragile antique. But the math tells a completely different story. At 100 GB written per day, which is genuinely heavy usage, a 300 TBW drive lasts over 8 years. Most users write closer to 10 to 30 GB per day, which pushes theoretical lifespan into the decades. And here's the kicker. SSDs don't instantly die when they hit their TBW limit. The warranty ends, but the drive often keeps working well beyond the rating. Real endurance torture tests routinely show drives exceeding their ratings by 2, 3, even 5 times or more. Meanwhile, actual users were out there disabling Windows indexing, turning off browser caches, moving page files to slow hard drives, all in the name of saving writes. The result was slower systems without any meaningful lifespan extension because the wear they were so afraid of was never going to happen in the first place. For most people, your SSD will be obsolete or replaced for capacity reasons long before you write enough data to kill it. But if you think understanding storage endurance is confusing, wait until you hear about how many people assume a new router automatically upgrades all their old devices to the latest Wi-Fi speeds. Wi-Fi generation compatibility. Buying a Wi-Fi 6 router and expecting your old laptop to suddenly get gigabit wireless speeds is like buying a sports car and wondering why your commute is still slow when you're stuck in the same traffic. Wi-Fi is a two-way conversation, and if one side is speaking a different language, you're not getting the headline features no matter how expensive the router was. Here's the thing. Wi-Fi 5 commonly achieves around 867 Mbps to 1.3 Gbps in real-world setups, while Wi-Fi 6 can theoretically exceed 9 Gbps. Sounds like a massive jump, right? But your 3-year-old laptop with a Wi-Fi 5 card doesn't care what the router can do. It's still negotiating at Wi-Fi 5 speeds because that's all it speaks. Most laptops ship with 2S2 radios that cap link speeds at 1.2, 2.4 Gbps anyway. So even if both ends support Wi-Fi 6, you're nowhere near the box's claimed maximum. Older devices stuck on Wi-Fi 4 or 5 see exactly 0 generational gains from your router upgrade, and that's before the real world gets involved. Congested apartment buildings with dozens of overlapping networks, thick walls, and metal framing can reduce a theoretical 2.4 Gbps line of sight link down to 200, 400 Mbit as 2 rooms away. At that point, the generation label matters less than whether your neighbor is also streaming and gaming on the same channel. Upgrading the router alone delivers incremental improvements at best unless you also refresh the client hardware, which most people don't. But at least Wi-Fi generation mismatch is predictable, unlike bandwidth versus signal strength, which is a whole separate disaster. Signal strength versus bandwidth. Your Wi-Fi icon shows full bars, yet your stream still buffers. You buy a range extender, position it perfectly, and nothing changes. You solved the wrong problem. Signal strength tells you how loud the router is shouting. Bandwidth tells you how much data gets through. Those aren't the same. Think of someone yelling in a crowded restaurant. They're loud, you hear them, but you can't understand them because 20 other people are also yelling. That's your Wi-Fi. Full bars mean the router's voice reaches you. It doesn't mean the channel is clear. Here's where the numbers expose the lie. A device at 50 dBm excellent signal pushes only 50 to 100 Mbit/s on crowded 20 MHz channels with 15 neighbors fighting for airspace. Meanwhile, a device at 70 dBm, a weaker signal, hits 200-300 Mbit/EUS on clean 80 MHz channels with zero interference. Signal strength is loudness, bandwidth is clarity. Protocol overhead makes this worse. Your router negotiates an 866 Mbit/s link rate. Sounds fast. After headers, acknowledgements, and invisible handshaking, actual throughput tops out around 400-500 Mbit/s, best case. Now add other devices. Every phone, tablet, and smart bulb sharing that access point cuts your slice smaller because fairness algorithms distribute airtime, full bars throttled by gadgets. The real kicker is misdiagnosis. People see stuttering videos, check full bars, and blame their ISP. The culprit is often channel collision. Your neighbor's routers on the same channel, packets smash into theirs, forcing retransmissions that tank your speed, or your ISP throttles certain traffic which has nothing to do with signal strength. But because the bars look good, you never suspect the real enemy. At least your Wi-Fi problems stay confined to one room. Wait until you realize how every millisecond of delay from your mouse, keyboard, game engine, and monitor quietly stack into a lag spike you blamed on the server. Every gamer has felt it. That weird floaty sensation where you move your mouse and the crosshair drifts like it's stuck in molasses. You blame the monitor, you blame the game, but the real culprit is a chain reaction of invisible delays stacking up behind the scenes. Input latency stacking. Here's the thing about latency. Every single step between your finger clicking and the pixel updating on screen adds a tiny delay, and those delays stack. A wired gaming mouse hits the USB port in 1 to 2 milliseconds. Pretty fast, but if you're using Bluetooth, that number explodes to 10 or even 20 milliseconds. Why? Because Bluetooth was designed to sip battery power on your earbuds, not to win a firefight. Now add your display. A 144Hz monitor updates every 6.94 milliseconds. A 60Hz screen takes 16.67 milliseconds per frame, plus another 5 to 15 milliseconds of processing lag. So let's do the math on a typical bad setup. Your Bluetooth mouse eats 15 milliseconds. Your Bluetooth keyboard adds another 15. The game rendering pipeline takes 30 to 40. Your 60Hz display tacks on 20. You're now staring down 70 to 90 milliseconds of total end-to-end latency. That is nearly a tenth of a second of floaty agony. And here's the real punchline. Upgrading just your monitor to a buttery 144Hz panel barely dents that number when your wireless peripherals are injecting an entire delay sandwich into the pipeline. Proprietary 2.4 GHz wireless gaming gear nearly matches wired latency, so the fix is simple, but the mistake of ignoring the entire chain is expensive. But if you think Bluetooth delay is frustrating, wait until you see how much money gets wasted on fake gaming network features. Gaming network prioritization, gaming routers and network cards love to promise lower ping through traffic prioritization, wrapped in buzzwords like AI optimization or game accelerator mode. Here's the thing, these systems are basically a local traffic cop directing cars at an intersection. They can control which packets leave your house first, but they have zero authority over the rest of the highway once those packets hit the internet. Quality of service, or QoS, works by managing the queue on your router's upstream link. If you have a 10 Mbit per second upload and someone starts seeding torrents, that link saturates, causing game packets to wait their their turn. Without prioritization, your ping might spike from 40 milliseconds to 300 because every packet is treated equally. QoS can bump gaming traffic to the front of the line, restoring your ping to baseline. That benefit is real when your upstream is choking, but here's where it gets limited. If your baseline ping is 60 milliseconds when nothing else is happening, QoS cannot turn that into 20 milliseconds. That 60 comes from physical distance, routing through multiple ISPs, and server processing time, none of which your local router controls. All QoS does is prevent your own network from adding extra delay on top. It's damage control, not performance enhancement. On uncongested connections, the impact is minimal despite all the gaming labels. Many fiber or cable plans offer upstream bandwidth that rarely gets saturated by typical use, so there's no queue to optimize. Now, ISPs often strip priority tags beyond the first network hop, and there's nothing it can do about server-side overload or backbone congestion. The invisible lesson here is that systems have boundaries. Understanding what a technology can and cannot do prevents you from spending extra money on features that sound impressive but can't deliver what you need. Yet, if you enjoyed this video and want to see more,